Today, we're diving into a technology that feels like it's pulled straight from science fiction. It operates on the weird, wonderful rules of the universe itself. We're talking about quantum computing. Now, this isn't just a small step forward. It's a complete shift in how we process information, and it promises to change, well, pretty much everything. So let's get into what that actually means.
This quote right here, it really nails it. We are not talking about a slightly faster version of the laptop on your desk. Nope, we are talking about a machine that can look at a problem from every single possible angle, all at the same time. Imagine trying to find a needle in a haystack. A normal computer checks one piece of hay, then the next, then the next. A quantum computer checks every single piece of hay all at once.
All right, so to really get how that magic works, we've got to start with the absolute fundamentals. What is it that makes a quantum computer so profoundly different from the classical computers we use every single day? It all boils down to one thing: the qubit. You've probably heard the analogy of a spinning coin, right? A normal computer bit is like a coin lying flat. It's either heads or tails, a 1 or a 0. A qubit is like that coin while it's still spinning. It's kind of both heads and tails at the same time. But here's the kicker. The real power isn't just that it can be both, it's what we can do with that potential. The dimmer switch is another fantastic way to picture this. A classical bit is just a light switch. It's either on or it's off. Simple. A qubit, though, is that dimmer switch. It's not just on or off, it's that whole spectrum of possibilities in between, and it can hold all of them simultaneously. That ability, that is the first key to its mind-bending power. And that power really rests on 3 strange pillars. First, there's superposition. That's our spinning coin state. Then you've got entanglement, and this is where it gets really weird. Einstein called it spooky action at a distance. You can link 2 qubits together, and no matter how far apart they are, even across the galaxy, what happens to one instantly affects the other. And finally, you have interference. This is the secret sauce. It's like noise-canceling headphones for a math problem. It cranks up the volume on the correct answer while all the wrong answers just cancel each other out into silence. Okay, so that's the theory, but how in the world do you actually build one of these things? Well, it's a colossal engineering challenge, and right now, the industry is basically split between 2 main approaches. The whole industry is grappling with this fundamental trade-off: speed versus stability. On one side, you've got players like IBM and Google using superconducting circuits. These things are incredibly fast, but they're also incredibly fragile. They have to be kept colder than deep space to work at all. On the other side, you've got companies like IonQ and Quantinuum who are literally trapping individual atoms with lasers. These are super precise, very stable, but a lot slower. It's a classic race between the hare and the tortoise. All right, so we know what they are and kind of how they're built, but what are they for? Let's be really clear here. These are not going to replace your smartphone for browsing Instagram. These are highly specialized tools designed to solve very specific, very, very hard problems that are basically impossible for any normal computer. The software for these machines are quantum algorithms. Some are legendary, like Shor's algorithm, the one that gives security experts nightmares because it can crack most modern encryption. Or Grover's algorithm, which is like a search engine on steroids. But honestly, in today's era of noisy, error-prone machines, the real action is in hybrid algorithms. That's where you cleverly use a classical computer for the easy parts of a problem and save the quantum computer for the bit that it does best. It's a team effort. And this isn't just theory. Major companies are already putting this stuff to work. Moderna and IBM are simulating molecules to design new drugs. Boeing is modeling new materials to build better planes. JP Chase is optimizing complex financial portfolios. And get this, Volkswagen even used a quantum computer to optimize traffic flow for buses in Beijing. This is happening right now. But like any revolutionary technology, there's a flip side, a dark side. Because the same incredible power that can help us discover new medicines can also be turned into a weapon. One that poses a profound risk to our entire digital civilization. And this is the stark reality. Shor's algorithm, the one we just mentioned, it's specifically designed to solve the exact math problems that form the foundation of our modern digital security. We're talking about everything: your online banking, your private messages, secure government communications. All of it could one day become completely vulnerable. And here's the really chilling part. The threat isn't years away. It's already here. Right now, adversaries are capturing and storing massive amounts of our encrypted data. They can't read it yet, but they're stockpiling it, just waiting for the day they get their hands on a quantum computer powerful enough to crack it all wide open. So it forces us to ask a really uncomfortable question. All that data we're creating today, our private emails, our medical records, our financial information, is any of it truly safe in the long run? This threat has kicked off a frantic global race. On one side, it's a race to build these powerful quantum machines, and on the other, it's a desperate race to build defenses against them. Our main defense is something called post-quantum cryptography, or PQC. The best way to think about it is as a brand new kind of digital lock. It's built on different math problems, ones that are believed to be hard for even a powerful quantum computer to solve. And yes, the top minds in cybersecurity are working around the clock to develop and standardize these new quantum-proof defenses. And make no mistake, this isn't just a corporate competition. It's a full-blown geopolitical arms race. You can see the kind of money we're talking about here. Nations are pouring billions into this field because the stakes for economic leadership and national security are absolutely enormous. But to unlock that future, the entire industry is facing one massive hurdle. And it's not just about getting more qubits, it's about quality. The physical qubits we have today are just too noisy. They make too many mistakes. So the next great leap, the real challenge for everyone, is to bundle thousands of these fragile physical qubits just to create a single, reliable, error-corrected logical qubit. That's the mountain everyone is trying to climb, using thousands of faulty parts to build one perfect one. So in the end, we're left with a race on two fronts. A race to build a machine powerful enough to cure diseases and design new materials, and a simultaneous race to build defenses against that very same machine. The real question isn't just who will win, but whether we can manage to build the shield before someone perfects the sword.